All right, hello class. Today we're going to take a look at how gravity affects the motion of falling objects. Today in class you're going to need a calculator, a formula sheet, and then also something to take a few notes with. All right, so gravity. How does gravity affect the motion of falling objects? Let's start off with a question. We just finished up a unit where we've learned to use graphs and motion diagrams and words to describe the different features and aspects of motion. And so let's consider what a velocity versus time graph might look like for an object that's freely falling. If we're allowed to ignore air resistance and just assume that gravity is the one thing that's acting on the object to make it move or to change its motion, then what might that look like on a velocity graph? So what I'd like you to do is pause the video for a second, use a scratch sheet of paper or a whiteboard, and just sketch out what you think that velocity graph might look like, and then we'll check our answers with each other and see what the results are. All right, I hope you had a second to write down or sketch a graph of what you think the velocity would look like as the object falls. Let's go ahead and see what this might look like. The first thing we want to do is establish which direction is up and down, and assign positive and negative values for those things. So typically in physics, we're going to say that the positive direction is up and the negative direction is down. So we'll just indicate that there here on the graph. If we've got an object that's moving left or right, then right is typically the positive direction and left is the negative direction. But we're dealing with an object that's falling, so it's moving up and down in the vertical direction. So it's important to establish this notation early on before you start to analyze a situation or a problem. And so we're going to say that down is the negative direction. We know that when we drop an object, it falls in that downward direction. And so we would expect it to have negative velocity as it falls. Okay, we're going to drop this object. So one of the important things to recognize is that when you drop an object, you give it a very specific value at the beginning of the problem for its velocity. You give it a zero velocity. And that's one of the things that physicists love to do, is to drop objects, because it eliminates that initial velocity that we might have to worry about otherwise. And so if we give it zero velocity by dropping it, then we can ensure that we're always starting right here at the zero velocity mark on our graph. And from there, we would expect the object to fall, and as it falls, it speeds up. It's going to accelerate. And so we're going to see an increase in speed in that downward direction. And that increase in speed on a velocity graph is going to look like a line that extends downward below the x-axis. And as we learned in previous lessons, the slope of this velocity versus time graph represents a very important feature of motion, which is the acceleration. And so we'll learn more about the acceleration today that gravity provides objects as we learn more about free fall motion. All right, another question to consider. Could the velocity of an object be zero at the same instant that its acceleration is non-zero? Okay, in other words, could an object be momentarily at rest but still be accelerating? And so this is a question that for a lot of students, their initial instinct says, well, no, that doesn't seem to make sense. How could something be not moving but accelerating? And so what I'd like you to consider is an object that you throw up into the air. Suppose you take a ball or an apple and you throw it up in the air. Well, what's going to happen to that ball? It's, as it goes higher and higher, it's going to be slowing down. Eventually, it's going to reach that highest point. And then at that highest point, something happens. It stops for just a second, just a moment, and then it turns and starts to fall back down. As it falls, it begins to speed up. On its way up, it was slowing down the entire time, and so it's accelerating. The entire time it's accelerating. As it slows down, even as it stops, and then as it falls back down and continues falling faster and faster on the way back down to the ground, it's accelerating. So the answer here is yes. An object most definitely can have zero velocity, but still be accelerating. And that's typical for objects that are thrown up in the air. All right, so what happens when you drop something? As we all know, gravity is going to pull things downward towards the ground. That's what keeps us on the ground. And as it does, it causes objects to accelerate. The acceleration of gravity is a constant value. The value is 9.81 meters per second squared. And because acceleration of gravity is always downward, we can approximate this value to help simplify some of the calculations that we'll need to do in our class, and we'll just round it to 10 meters per second squared. And again, because it's in the downward direction, and we typically assign that direction as the negative direction, we'll just use negative 10 meters per second squared for our calculations. All right, when something falls with only gravity acting on it, there's a particular term we use to describe these situations, and that's free fall. Now, it's important to recognize that gravity can be the only influence on an object if it's considered to be freely falling. And so this is a situation that doesn't show up too often in real life, because in real life we're dealing with things like wind and air resistance, and those are influences that are not going to allow an object to continue accelerating as it falls. And so we do want to assume at times when we're learning about physics what it would be like if there were no influences except gravity. And so that's what we'll learn today. It says, what would you expect if you dropped an elephant and a feather at the same time? Okay, well, obviously, if you could imagine that, you would expect the elephant to fall and probably hit the ground much sooner than the feather would. Okay, and so as the feather falls, it takes a little bit longer there for it to hit the ground, as the animation on the right shows. And so for the longest time, physicists and scholars, predicted that the reason things were falling faster than others was because they were bigger. Scientists like Aristotle back in the day would have hypothesized that the larger the object is, the faster it falls because of its mass. And it took years before that idea, before there was a shift in our thinking. And it took the work of a person by the name of Galileo to eventually reveal that there was something else at play here besides mass, that mass was, in fact, not a factor. And so what we find is that if we could turn air off, if we could eliminate the air from the room and keep air from being a factor, then we see a completely different picture. And so Galileo predicted that without air, if we were in a vacuum, that the elephant and the feather would fall at the same rate, that gravity would affect them in exactly the same way. They would accelerate at the same rate, and they would hit the ground at the same time as they fall together. So this was not something that was easy to prove. It was a hypothesis that Galileo had, and it took lots of experiments and a lot of different trial and error type of activities for him to reach this conclusion. And so because we can't just eliminate the air from the room very easily, it's difficult to test an idea like this. So where could we find a place like this, though, with no air resistance? Oh yeah, the moon. The moon would be a great place, because we know that there's no air on the moon. Maybe we could test this out. And that's exactly what they did on one of the early Apollo missions. They didn't take an elephant with them, but they did take a hammer and a feather, and watch this. All right, so indeed Galileo was right, and we've since conducted many other investigations, many other experiments to confirm what he believed a long time ago. And in free fall, the initial velocity of the object is going to be zero. Again, when we drop an object, we can set that initial velocity as zero by ensuring that we're not throwing the object downward or throwing it up or giving it any type of initial velocity. And since this is uniform accelerated linear motion, we can use kinematic equations to help analyze the motion and how it changes as these objects fall. In the real world, objects that fall will reach a point where the drag force or the air resistance force will equal the force of gravity. And at that moment, the object will stop accelerating. It just continues to fall at the same speed. That speed is, there's a term for that known as terminal velocity. That means it's the final speed an object can reach due to air resistance. Again, without air resistance, objects would just keep falling faster and faster and faster. But because of air resistance, terminal velocity is a thing, and so it's the reason a person can, parachute from a plane and use their parachute to slow down their descent, and then as they fall, they just continue to fall without the fear of having to speed up and crash into the ground. Some example problems. So we're going to work through a quick example problem here. It says, how fast would a dropped apple be moving if it were allowed to fall for 2.5 seconds? All right, so as we do in physics, we're going to go through and identify the information in the problem that's given to us. For this problem, we're told that the object is allowed to fall for 2.5 seconds. So that's important information we want to write down. We're going to call that the time. We'll assign that the value t, the variable t. So time is 2.5 seconds. And then what else do we know about this situation? We know that the apple was dropped. The word dropped here is very important because, again, when we drop things, we're establishing a very precise value for our initial velocity. We're saying that initial velocity is 0. We don't have any downward velocity for the object whenever it's dropped. It's not until it's allowed to fall that it reaches some faster velocity. And then the last thing that they don't tell us, but we know now because of our understanding of gravity, is that gravity has a very precise acceleration equal to -10 meters per second squared. All right, and we're asked to figure out how fast. So we want to know how fast is it falling after that time period. So it's the final velocity that we're looking for. All right, so we've identified the information that was given to us in the problem. We've got the time, we've got the initial velocity, we've got the acceleration. We know we're looking for final velocity. So at this point, we need to take a look at our formula sheet and decide which equation we're going to use. So we've got these three equations on the formula sheet. For my formula sheet in our class, it's equations 4, 5, and 6. But if you're using a different formula sheet, you'll find these equations also. These are known as the kinematic equations, the three equations that help describe things like initial velocity, acceleration, time, and displacement. And so for this question, we want to pick the equation that incorporates those four variables that we're working with: time, initial velocity, acceleration, and final velocity. And so as you look through these, we look at the first one here, number 4, and we notice, okay, here's a equation that will let us solve for the final velocity given the initial velocity, the acceleration, and the time. So that's exactly the one we want to use. And so we'll write that down. Final velocity, VF, equals initial velocity plus acceleration times time. Okay, and we substitute in the values that we have from the problem. We're looking for the final velocity. The initial velocity was 0 because we dropped the object. And then we know that acceleration is going to be -10 meters per second squared because gravity accelerates objects at that rate. And this object was allowed to fall for 2.5 seconds. And so as we solve for final velocity, we find that we get a negative answer, -25 meters per second. So what does the negative sign mean? The negative sign means that as this object falls, it's falling in that downward direction, that downward negative direction towards the ground. And so that's one example of how we can use a kinematic equation to help analyze a situation that involves a falling object. There are several other types of problems we could be asked. We can be asked, how long does it take for an object to fall? We could be asked, how far is the fall? What is the height from which something was dropped? But this will give you a good start as we start to learn about free fall motion and how gravity affects